Hey everybody, and welcome back to Calc 3 Online. So I just want to do a few triple integral problems. Can't hurt to see some more worked examples. Nothing new in this video. Just know that these things can be kind of hard when you first see them, so I wanted to do a few more examples with them. So this first one just asks you to integrate xy over the volume enclosed by the plane z equals x plus y, z equals 0, and between the surfaces y equals x squared and x equals y squared. So, a lot going on here. So I'm going to start with maybe these two things. So I do think it's good to start trying to wrap your head around what is going on, okay? So for y equals x squared, okay, if this is my standard 3 coordinate system, that is going to look like, so that would be x squared kind of down in the plane I'm trying to show. And then if I like extended it, right, into 3 dimensions, right, I get, so there's no restriction on z, so you just sort of get that forever and ever. That's what, and like it would go down too, right? You would get this going down. So that is what y equals x squared looks like in 3D. X equals y squared is basically just like the similar thing, but it's for the root function. So I'm actually going to give myself a little more room. So it's like you have a square root in the plane, but then again, you kind of let it go forever up and down. So they're very hard for me to draw, but it honestly is probably easier for me to draw what that would look like in 2D. So if I take 2D-dimensional object here, y equals x squared, right? I can draw that one. And then we'll do purple. X equals y squared it's really like, I guess, fully, it's not a function, right? It's like x equals y squared is a parabola on its side, but we really only need to know the intersection spot. So these two graphs, they intersect there at 1, 1, that's this point. And so we're interested in that little part down in the plane. And so you got to kind of think of that coming out of the page right now. And it, z equals 0 is this part literally right here, but we go up to z equals xy. So it's kind of like you take this surface, this little weird chunk, and eventually you're just going to like cut it off with that plane, okay? So to set this up with a triple integral, we don't really need to do any coordinate swaps or anything. I would just do it at like normal. So I'm just going to do like a dz, dy, dx. This thing is a type 1 and 2, so it really doesn't matter if you do dy, dx, or dx, dy. I'm just doing it as like a type 1 in the plane. But I would definitely do dz first because we have these bounds basically for z right here. We go 0 up to that plane, x plus y. So 0 up to x plus y. And then y, like if I'm doing my y bounds, I go from the blue up to the purple, right? So that would be, the blue is x squared, right? And I go up to square root of x. So that's my y bounds, my z bounds I got. And then x, actually, or y, like this is where the number part comes in, but these intersect at 1, 1. So you would just go from 0 to 1, right, for x. And so that is the bounds, which is usually probably the hardest part, I'd say. Integrating is not so bad. So I'm going to kind of try to speed through some of this part. So the first integration, you just get a z, then you do x plus y minus z at the bound, so you get like xy times x plus y, dy dx, x squared, square root of x, and then 0, 1. And then I would probably just distribute this thing in. And so I would get x squared y plus xy squared dy dx. Again, same bounds, haven't done anything with that. Then you you get like a bunch of annoying algebra now. So if you do out the integration, right, you're going to get like, for dy, you're going to get y squared over 2 and then y cubed over 3. Then you actually do have to like a lot of times we're kind of used to zeros and stuff here, but we don't have that here. So you actually do need to do like plug in the bounds for y for this and then do minus this one. What that kind of looks like if you go through and do it is x squared x over what was it? X squared x over 2 plus x to the 3 halves over 3 minus x squared x to the 4th over 2 minus x to the 6 over 3 dx. So trust me, raise that to power, divide by it, raise this to power, divide by it. You can see I've got like, this one over 2 and then this one over 3, and then I'm subtracting the other one once I plug in those bounds. So then I would you can combine a lot of those and whatnot. If you do that integral out, you get x to the 4th over 8 plus 2x to the 7 halves over 21 minus x to the 7th over 14 minus x to the 8th over 24 goes 0 to 1. You get a 4th plus 2 over 21 minus 14 minus the 24th. And all of that should equal 3 over 28, if I did my math correct. So honestly, at this point, it's just a lot of annoying polynomial integration. But this is setup, I think, is probably like the part that I really, really, really want you to see. All right, so this one, you're asked to integrate the triple integral of just x dv over E, where E is the region bounded by z equals 0, z equals x plus y plus 5, and then these two cylinders, x squared plus y squared equals 4, and x squared plus y squared equals 9. So if you're doing cylinders, it probably makes sense to think cylindrical coordinates, and that's what I would do. It usually will be easier if there's cylinders involved. I want to try to draw this one too, just so you kind of get an idea what it looks like. So you've got a cylinder with a radius of 2. Okay, let's say that's my cylinder with radius 2. Right? Then I've got another cylinder of radius 3. So let's say that one, right? And then what's happening is, so you're integrating, your region is sort of like between the two cylinders in here. It's like a cylindrical infinite donut thing. But then you have this added thing with this plane, right? Because you do start at z equals 0. But then with the plane, what happens is you're sort of going to cut off a point, right? And I cannot draw these things, but like basically there's like a slash somewhere where you sort of cut it off. And the idea is like, there's some sort of angular plane, x plus y plus 5, that would cut that donut thing off. So that's sort of, if you can make some sense of what I'm drawing there, what we're integrating over. Definitely makes sense to do cylindrical because you got cylinders involved. So I'm going to switch it over to cylindrical coordinates, okay? X will then become r cos theta. And then remember so now I can actually use the word Jacobian. You have actually, never mind. I've said something that I didn't mean to say yet in these videos. This is the problem with planning way out. You haven't learned about Jacobians yet. You will soon. Don't worry about what that word means. You're going to learn about how this R thing that pops up is something called a Jacobian. But don't worry about that right now. So you have x is r cos theta, and then you have an extra r, and then you have we can do like dz dr d theta. And z is going to run, it's my vertical distance. We're going 0 up to the plane. X plus y plus 5 would also convert to r cos theta what was it, r cos theta plus r sine theta plus 5. And then r goes 2 to 3, right? Because it's the radiuses of those circles. Right? So 2 out to purple, 3 out to orange. And then we need to go a full 2 pi. Right? We're going all the way around the cylinder. So the first integration is not so bad. There's no z's, right? So we can just do this bound minus 0, right? So we'll have 0 to 2 pi, 2 to 3. And then I'm also going to combine these r's. So we got r squared cos theta, and then we're multiplying it by r cos theta plus r sine theta plus 5 dr d theta. Okay. Then comes kind of some annoying stuff. You've got to multiply, like I would distribute all this in, and r is going to be actually not so bad yet, but the part that's going to be annoying is you will have to deal with doing a subtraction of the bounds because of the 2 and 3 here. So so what that is going to look like is I'll pause the video and I'll put down what that would look like. Okay, so I did a few things there. I would distribute in, right? So I get like r, times r is r cubed, and then cosine times cosine is cosine squared. That's where I'm getting that. Cosine times sine, cosine sine. Cosine times the 5 thing is why it's just cosine. And then I also integrated the polynomial stuff with r. So I did like r cubed going up to r over 4 over 4. That's where that 4 is coming from. That's 4. And then I also did all the plugging in of the bounds 3 and 2. And so you can kind of see this is plugging in the 3, and this is subtracting the 2, right? A lot of straightforward stuff, just a lot to keep track of, okay? So now what I would do is I would use some trig identities. So integrating like cosine squared can be a lot easier if you use the identity cosine squared equals 1 plus cosine 2 theta. So cosine squared theta equals 1 plus cosine 2 theta over 2. And so what I would do is I would basically multiply the 4 by 2. So I'd have 81 over 8, and then I'd subtract like 4 over 2 or 2, right? And then that's how I would simplify these ones. Then I would also simplify these ones. I would use an identity. So 2 sine theta cos theta is sine 2 theta. And any of these kind of things like cos 2 theta or sine 2 theta, they're really easy to integrate because you can just do like, you just divide by the number inside, right, and change up to plus or minus the trig function there. So I would also use this. So we would need to basically do sine 2 theta divided by 2, right? So again, I would do like 81 over 8, and then I would do minus 4 over 2 or 2. So if you do that, you can simplify that big mess, combine like terms, and get this. And then all of those things are actually quite nice, right? When you integrate sine 2 theta now, right, you can just, it's going to be negative cos 2 theta over 2 and stuff like that. So this one would be sine 2 theta over 2. So a lot of these are really nice and easy to integrate now. So at that point, I'm going to kind of let you fill in the blanks. You should, once you plug in the bounds 0 and 2, you do need to do all the subtraction and stuff. You should be getting 65 pi over 4. That's what you should get. But that's a good example to show where cylindrical coordinates comes in really handy. So I don't want to do this one fully out. I will write down the answer, but I just want to show how we could take this thing and convert it to spherical coordinates. And you might think to do that because of this part right in here, right? If you convert that to spherical coordinates, it'll be rho squared. So we basically need to figure out what kind of region we're working with, right? If I look at these two, you can see that, this is equal to x. So if you do x squared is going to equal 9 minus y squared, so then x squared plus 9y squared is 9. So basically there's a circle of radius 3 involved, but we're only concerned with really the first quadrant because we're saying a y is going 0 to, what was it saying, 0 to 3, and x is going 0, so x equals 0 is the vertical line, to the circle. So we're really only concerned with the first quadrant there. And so that's kind of what we can imagine what's going on in the plane. Like if you projected it down to x and y, that's what you get. This stuff, okay, so this is a little maybe trickier. Z equals the square root of x squared plus y squared is, it's 3D, I was drawing a plane. So that is a cone, okay? It's a nice kind of cone in the sense that it's, this is basically like a y equals x kind of line. It's like the one that's smack dab halfway between here and here and here and here. So it's a circular cone, kind of the nicest one. And then this is a sphere. So that thing, it's getting a little messy. So this part is a sphere, and it's a sphere centered at the origin, right? Because you could set it equal to x and then get rid of the root. And it has a radius of the square root of 18. That radius is the square root of 18. So what you got to kind of put together is it's like this region extended up and between this and the sphere. The sphere is going to act as kind of the outer surface, okay, because it's the upper bound there. So imagine putting this kind of encapsulate the cone, but then you're not considering the whole sphere, you're not considering this whole thing, you're only considering the part like here in the first quadrant that kind of extends up into those two. I'm not going to attempt to draw it because I won't do a good job. It won't turn out well. So, that is basically enough to put this into spherical. We're going to have a rho squared from this part. We have to have a rho squared sine phi from, that's like coming up as the, in the dv when you do the integral, when you convert to spherical. And then we'll have like a d rho, d theta, d phi, okay? And the rho is going from the, we do have 0, right? 0 right here, 0 right here. And the outer thing is the sphere. So my radius kind of measurement is 0 out to the square root of 18, okay? And theta is, the polar angle, and you can see it really well here. If you use that polar angle, you can see it's 0 to pi over 2. And then the last one is the angle that pops down from z, and that would be dictated by the cone, right? We want to come down, from here we want to go down to that, and since this is that nice cone that's like smack dab in the middle, that would be pi over 4, that angle. So the last bound would just be 0 to pi over 4. And then you can go and integrate it. It's not horrible. I will tell you the answer if you want to go try and solve it. You should get 486 times the square root of 2 over 5, then pi squared for some weird reason. But I really just wanted to kind of cover the setup of that one. But I do think you should be able to solve this one out too.